Okay. Hello everybody. So in this video, what we're going to do is quickly do some basics of truss analysis. So this video is more like a refresher for truss analysis. So I'm not going to go into like super detail, but it'll give you a really quick overview in case you're trying to refresh your truss analysis. I would recommend actually looking up a good book if you're starting out with truss analysis. So when we're talking about truss, the main things we are looking at is truss stability, which leads us to statically determinate structure. So initially, the method of sections and method of joints, which we'll be covering next, is usually applied only to statically determinate structure. So what that basically means is you should be able to calculate the different parameters, basically the internal forces, using just the static determinate condition without considering any deflection into account. So let's talk really quickly about how we define the following. So we consider J to be the number of joints, which basically are kind of the nodes of the truss, M to be the number of members or links, C to be the total number of constraints, which is basically fixing the truss and so on and so forth. So this right here, excuse me. Okay. So this can be either horizontal or vertical. This actually represents two constraints. So this basically prevents the member from moving either in the horizontal direction or in the vertical direction. So it's like fully constrained. And then this one is basically just one constraint. So what that means is for this one, the particular object can move this way or this way, and this one can move up or down. So that basically constrains every other direction. So we will try to find the relation between J, M, and C. So if you have consider just a single joint, what it could potentially do is it can move either horizontally or vertically, right? So move horizontally or vertically. So that gives you basically 2 degrees of freedom. And what we want to do is, this is basically a plane consideration. So we want to basically add 2J corresponding to each joint. Each member is basically going to be between 2 joints. So if I have one joint over here, my left hand, and then the other joint over here, and then if I consider this scale ruler over here to be the joint member, so this basically prevents the 2 joints from moving relative to each other. They can still kind of rotate in the other axis, so you can basically move like this, 1, 2, and then 3. So we still have 3 degrees of freedom. So when they were just by themselves, they could potentially move like this and like this. So we have 4 degrees of freedom in total. Adding one link in the middle basically reduces 1 degree of freedom. So each constraint, typically, so if you have a joint node like so, my constraint is basically either going to fix it like here or like here, and then get rid of 1 degree of freedom over here. So the formula basically means that the total net degrees of freedom that we have is going to be 2 times J minus M minus C. And if this total degrees of freedom is equal to 0, that basically means that the structure is statically stable. So essentially it means it's locked in place, they can't be moving around. So what does that mean? So basically if this sum here is 0, that basically means the truss is stable and determinate. If this is greater than 0, the system is unstable. So basically there are more number of joints than the number of members and constraints linking them together. So there is basically the difference here, this number over here would give you the total net degrees of freedom. So for instance, if you consider this rocker arm mechanism, so you basically have here, like so, there's like here, here, and here. If we do this total, you'll notice that there is 1 extra degrees of freedom. So essentially if I do move this joint over here, so my structure is going to become like this. So there is 1 degree of freedom. So this is an example of a rocker arm mechanism. And if this value is less than 0, that basically means that the structure is still stable. But what happens is there are more number of unknowns in terms of the joint forces. So we need to use the deflection into account before we can actually calculate the truss values, truss internal force. So if you think about an alternate interpretation, if you consider a single joint, it basically end up with two equations, the x and y equilibrium for this joint. The link, or rather this basically provides 2 times j number of equations. So each link and a constraint is actually going to be an unknown force. So basically when these two numbers are equal, we would have same number of equations and unknowns. So we'll actually be able to solve our equation. If one is more than the other, so for instance, if you have more number of joints, so the joints could potentially move about, so that the additional degree of freedom would basically give you solve for the motion of your particular object or the joint. So we need to be careful when you're talking about truss stability. So if you consider this particular example, I could potentially, if you count the number of links and number of joints, so you will actually notice that this structure appears to be stable. So if you do the total over here, so here, how many joints do we have? So we have j equal to 4. And then m appears to be 4. And then c, basically this is 2 and this is 2 equal to be 4. So it looks like 2 times j is 8. So we get 2 times j minus m minus c would be equal to 8 minus 4 minus 4. So you would actually think, or if you just do a blind application of the formula, you would think that the structure is stable. But in reality, I can basically pull on this particular link like so, and then the entire structure is going to rotate down. So this will basically go like this. I mean, this is fairly, oops. So like so. I mean, this is evident when you just do a really preliminary analysis, but it's still good to be aware of this and then not apply this formula blindly. Okay. So when we talk about statically indeterminate structure, what do we actually mean? So consider the spring example over here. So what I'm going to do is imagine I'm cutting the spring at this bleed location. And what I'm going to do is try to solve for the internal forces in the spring. So how would I do that? I can basically say this whole structure over here needs to be in equilibrium. So the only way I can do it is to make this force equal to this force, right? So that's the only way I can do it. So this internal force essentially needs to be equal to F. And so this is basically coming from my static equilibrium. Now consider this example when if I have basically two particular joints over here. So what that basically means is that if I try to solve this, I'm going to cut it over here. So if I solve this, I basically have one unknown over here and then another unknown over here. So you can basically think of this as being F1 and F2. If you think about just having the x equilibrium, so there is no forces in the y direction, so there's no point doing that. So our equilibrium is going to basically be F1 plus F2. This needs to be equal to F. This is great, but then now you run into trouble because you can't actually solve for both of these. You can calculate the sum of these two forces, but you cannot calculate them individually. So the way we would actually calculate them is we need to have the deflection of the two springs. So we need to basically match the deflection of those two springs. So if this value is K1 and this value is K2, the additional equation that we would have is that the deflection, which is basically going to be F1. Let me use a different color. So if I can basically say F1 divided by K1 needs to be equal to F2 divided by K2. So now we basically have two equations and two unknowns. So this is one in blue is going to be 1, and then the one in red is going to be 2. So right now we have these two equations and two unknowns. So by incorporating or invoking the deflection equation, we actually come up with an additional equation which we can use in our solution. Okay, so we will deal with the statically indeterminate case in the next video, where we would have to actually use the method of virtual work, which is basically the follow-up video. But in this case, we're going to basically look at a statically determinate structure and then try to solve for all the internal forces. I'm considering a really simple truss structure over here. Basically, it has many joints. So basically, this has 5 joints. I just number them 1, 2, 3, and then 4 and 5. And then I'm assuming I'm applying a 10 Newton force. And then all the links are assumed to be equal, and which basically means that this angle over here would end up being 60 degrees. Right, fairly simple structure. The first step we're going to do is try to create the static equilibrium for this. So notice that the first thing I do is get rid of the constraints. So I'm going to basically get rid of this guy and this guy. So when I do that, as soon as I get rid of the constraint, I need to support the beam structure, otherwise it's just going to fall off. So what I would do is basically, since this was fixed, I need to apply two forces, the vertical and the horizontal. This is just going to be a vertical force. So I'm going to basically apply a force here, and then we'll call this F1, and then this is going to be Y. Oops. So okay, so this is going to be F1Y. So Y, and then here I'm going to apply an X force. So this is going to be F1 and then X over here. Here I'm going to apply just the Y force. So this is going to be F4 and then the Y. So this is basically getting rid of the external forces. This is what we would do. The next step, what we can potentially do is actually solve for just the external forces alone. So the way I would do it is basically consider the equilibrium for the entire structure. So what I'm going to do is make the easiest way to do it is to consider the moment about one of the joints. So I'm going to basically consider either I can do a vertical equilibrium and a horizontal equilibrium, or I can basically do the moment of about one particular point. So if we take this particular example, if I do the Y equilibrium, I'll notice that the only force, if I do the X equilibrium, the only force that is there in the X direction is going to be basically be this F1X. So that basically gives me F1X, this needs to be equal to 0. And what the next thing I need to do is basically I have these two unknowns. The two equations I would have is basically the vertical equilibrium. I apologize for that, the timer. So this is basically going to be the Y equilibrium and then the moment equilibrium. It's actually significantly easier to actually do the moment equilibrium. So what I'm going to actually do is take moment about this particular joint over here. I'll just like clear the screen. So I'm going to take the moment about this point. So this is basically the only force that's going to be left is this Fy4, and then I'm going to measure this distance. So if this is 1, I'm not really concerned about the units. So this distance is basically going to be this. So if this is L, this is going to be L over 2, and then this is going to be the total distance is this is going to be 2L. So I'm going to get 2L times Fy4, and so this is basically rotating the whole structure in this direction. So this would be equal to what do I have? this is going to be basically be L plus 0.5, so there's going to be 1.5 L, and then times 10. This will basically give me F4 Y. Actually, I think I'm switching this Y4 and Y thing. This would basically be 7.5, and then I can just use the vertical equilibrium, and then I can calculate F1 Y to be 2.5. Right, fairly straightforward. So we'll basically use these values when we're calculating the next level forces. So for doing that, what we need to do is basically think about dismantling the truss structure, and what we do is basically draw the forces. So essentially what will happen is, since we get rid of this link over here, this is going to apply a force like so. This link would have applied a force like this. So both of these would actually be T12 in magnitude. Notice that basically I'm getting rid of this link, so I'm assuming there is a tension force like so. That's going to come here. Similarly, I'm going to apply a force here, here. So always my unknown force are going to be towards the other joint. So there's going to be T24. And then this one like so. Right, so this is going to be T45. And so on. So I basically complete this. So once I do that, I should end up with this structure over here. What I did was basically take the equilibrium about this node 1. So what are my forces? I'm going to consider the x equilibrium. There is x equilibrium. The only force that is there is going to be this F1x, and then this T13, T12. Both of these are actually in the same direction. So basically both of them are going to the right. So I use a positive sign. And then what I do is I'm going to basically take, since this is 60 degrees, I'm going to take the component of T13 along the x direction. So this is going to be T13 cos 60. That's basically this term. And then I'm going to get this is equal. This is the x equilibrium. I do the same thing for the y equilibrium. So the y equilibrium, you have this force going up, and then I'm going to resolve this force T13 along the vertical. So this is T13 sine. So that's what we get here. T13 sine plus F1y is equal to 0. What I do is, between these two, I don't know T13 and T12, so I can use this equation to solve for T13. I get it as minus 2.8868 because I already know this value, which is basically 2.5. And then what I can do is substitute this into this upper equation, and then I can solve for T12. Fairly straightforward. So we should be able to actually calculate these values. The next easier joint to do is actually T4, which is kind of very similar to 1. So if we do that, I'm going to basically keep my sign in track. So the horizontal equilibrium, I'm going to take T45. So that's going to be T45 cos 60, which is basically here. And then T24, both of them are in the same direction. So I get this equation over here. I do the vertical. Basically, this is going to be resolved as T45 sine 60, which is basically this term, and then F4y going in the vertical direction. So both of these have the same sign. Notice that even though my T24 and then the component of T45 are going in the negative y direction, I'm using the positive sign over here. The reason is I could potentially basically make both of these negative. So I can basically make this negative, and then this basically I can make this as negative as well. But my equation still remains the same. So I basically just pick the left direction for each equation. I could potentially choose a different direction as the positive direction, and it's not actually going to cause too much of a problem as long as you're just doing that for one particular equation. Think of just multiplying this by a negative number, so you're still good to do that. So once you do that, you can actually solve for T45 and T24 like so. The next joint we're going to go and solve is basically joint 2. Basically, we've already solved this guy. We have solved this guy. The two unknowns are going to be basically T23 and T25 at this point. So what we do is look again at the x and the y equilibrium. So this is the x equilibrium. We have T12. Right now I'm basically taking this direction, going left as positive. So T12 is going to the left. T23 cos 60 is going to the left, and then T24 is going to the right, and then T25 cos 60 degrees is also going to the right, and so I get this equation over here. I do the same thing for the vertical direction. T23 and T25, both of them, the sign components are going to be going in the up direction, so I choose upward direction to be positive. So the unknowns are T23 and T25, so I can basically solve them. From this equation, notice that they need to be equal in magnitude and opposite in sign. That's what I get. So T23 comes out to 2.8868 newtons, and then T25 comes to minus 2.8868 newtons. So at this point, if I look, so I basically solve for all like basically majority of the equation. So everything here I basically solved. So the only unknown right now is basically this T35. I can either pick joint 3 or a joint or node 5 or node 3 to actually make my solution. So that's what I'm going to do. Just pick node 3, put the equilibrium. I actually don't need both these equations, so I can just pick one of these. This equation is actually, either one would work. This equation is obviously simpler, and then I can basically solve for T35 over here. So once I do that, if you're really interested, you can just look up node 5 as well, and then look at the calculation. But what's going to happen is this is going to give you the final forces, which I've summarized in this particular slide. Okay. So the next one we're going to do is what's known as method of sections. So in the method of sections, what we do is, it's previously we were basically looking at equilibrium for the whole structure. What we're here going to do is think about taking a complicated structure and then cutting it at some particular point. So notice that this structure I basically added 2 more links, which wasn't too difficult for me to create the drawing. But this basically means that the structure is a little bit more complicated. So you have basically 3 more unknowns that you need to solve. It kind of gets a little bit annoying. So imagine I wanted to solve 3.5, which is over here, and I'm basically interested in that one particular force alone. I'm not interested in anything else. So if I want to do this, my analysis is going to be much longer, which is kind of a little annoying. So what I'm going to do is, instead of solving the forces at one particular node or one particular joint, so what I'm going to do is basically first solve for the external forces, and then just use the equilibrium really quickly, and then calculate by cutting the particular the truss structure at particular location, and then try to solve for the internal forces, because once you cut the structure, the internal forces kind of act like an external force. So the first step is to actually calculate the external forces. So if you do the x equilibrium, basically this part becomes 0. Next, what we're going to do is look at the equilibrium for x, basically gets rid of this. We can look at the equilibrium along y, which basically gives me f1y plus f4y. This needs to be equal to 0. And then the other thing I'm going to do is take the moment about one of these. So I'm going to take the moment about joint 1. So I'm going to call that maybe M1. So for that, we need to calculate. So if you assume each of this link is D or L, so this is going to be 1D, 2D, 3D. So this is going to be 3D. And my 10 newtons is basically acting, this is 1D, 2D, and then this is going to be D over 2. So if I do this, basically I would get 3D times F4y should be equal to 2.5 D times 10 newtons. So this allows me to solve for these two forces. I would basically get this F4 45, this basically becomes 25 over 3 newtons, and then this basically becomes 5 over 3 newtons. So now I have the external forces. Notice that these two add to 10 newtons, basically 30 over 3 is 10. So the structure is going to be in vertical equilibrium. So this is what we do. The next step that we're going to do is I'm going to cut this particular structure, and you need to be careful about where you're actually cutting the structure. So since I want to calculate the value for T35, what I'm going to do is when I cut the structure, I need to make sure that my cut basically passes through T3, the 35 link. So once I cut it, I can cut any of the other ones. So I can either cut it like so, or I can cut it like here. Either one would work. What I'm going to do is use the red one because it's a little bit nicer for me. So if I do that, this structure I'm going to imagine doesn't exist at all. So let's maybe just, I'm going to clear the screen. So I'm going to imagine I'm going to cut it over here. So basically this structure doesn't exist to me. It's kind of like dead to me. So if I look at this, what I'm going to do is basically I'm interested only in this particular force. I've actually already calculated these values, right? So I actually know this to be 0. And then this value, I believe I calculated that to be, give me 1 second. So we calculated this to be 5 over 3. So maybe I should redraw this particular structure. So when I do that, so I'm going to get up these forces. So what I'm going to actually do is I'm going to get this 35, T23, 312 over here, right? So what I'm going to do is I'm going to pick a point. I can basically take moment about any point. So I can take this moment over here. I can take the moment about here. I can take the moment about my next door neighbor's computer, but that's not very useful. If you look at this, notice that T12 and T23 basically pass through this particular node over here. So if I take this moment of the structure about the joint or node number 2, the component or the contribution of these two forces becomes 0, and then the only thing that I'm left with is basically the thing I'm looking for, T35, and then this is basically 0, and then this is known. So if I do that, I basically would end up with F1y times d minus T35 sine 60 degrees would be equal to 0, and then I can solve for T35 is equal to minus 5 over 6 newtons. So this is particularly useful when you want to calculate just like 1 or 2 forces. So if I wanted to calculate 2 forces, what I would do is basically say, for instance, I wanted to calculate T23. So what I would do is basically pick some other location, or what I can do is basically once I calculated 3.5 for this particular section, I can basically do the horizontal equilibrium, which basically means I would get T35, and then whatever this angle is, this is going to be 60 in this case, and then I'll get plus T23, and then this will be cos 60. This would be equal to 0, and then now I can really quickly calculate the value of T23 and T35. So this is particularly useful when you're doing finite element analysis, and then you just want to double check your calculation for a few 1 or 2 particular forces rather than actually trying to solve the whole structure. Again, both of these would end up being equivalent, so the calculation that you do with the method of section should actually ideally give you the same result as the calculation you do with the method of joints. So this basically concludes our quick analysis on trusses. Basically what we did was really quickly, we talked about stability and then stability of truss structures. The next thing we did was talk really quickly about what is it meant to be statically determinate and statically indeterminate, and then we talked about method of sections and method of joints. So this basically concludes our video here.